When I was younger, I loved to ask elder astronomers, what was the most amazing discovery of your lifetime? The first few times I expected answers like dark matter or pulsars or some other exotic something. I very quickly learned that the elders of my profession would consistently reply, galaxies. It put a perspective on things for me. Galaxies are one of the most fundamental building blocks of our universe. But there were folks early in my career who predated our modern understanding of these starry islands. As I look around and find myself firmly planted in middle age, I've started to wonder what I'll look back on as the most remarkable discovery of my lifetime. As of today, my answer is dark energy, but I'm hoping that isn't my final answer. Right now, humans are tantalizingly close to being able to search for life on other worlds where it is reasonable to think life could exist. We can't do it yet, at least not in a way that would be safe for any potential life, but this is a long game. And as we'll discuss today, the technologies we need are being actively developed and tested on Earth. And the missions we need to find the best places to search are either already out there doing their job or are preparing to launch. This could happen, provided nothing happens to prevent us from getting off the planet. Today, we're going to discuss the search for life on other worlds, some of the problems with humans being alive in space, and our space junk, and how it can make all of these things harder if we aren't careful. All this and more is coming to you here on Escape Velocity Space News. I'm your host, Dr. Pamela Gay, and I'm here to put science in your brain. Humans are messy. Take that statement however you want. Human beings are meat sacks of emotion with thumbs. We're capable of making great works of art, magnificent computations that describe our universe, and disgusting messes of pollution that wreak havoc on our ecosystem. We've got range. The messes humans make have actually started to build up not just on Earth, but also in orbit. It's estimated by the European Space Agency's Space Debris Office that there are 1 million objects in orbit between 1 and 10 centimeters in size, and 130 million objects between 1 millimeter and 1 centimeter. Each of these objects has the potential to hit a satellite and cause some degree of harm. Add in the 36,500 objects larger than 10 centimeters, an Earth orbit can be seen as a swarming mass of materials with an ever-increasing probability of collision. And that kind of collision can lead to what is called the Kessler syndrome, where objects start colliding in a cascading series of events that cause objects to fragment, and those fragments fly off in random directions such that they turn into more collisions and more fragmentation of additional objects in a chain reaction that creates so much debris that it is no longer possible to safely launch spacecraft off our planet. This is a future that would make it impossible to replace weather communication satellites or reduce our ability to monitor our planet for everything from hurricanes to volcanic eruptions in remote locations. In a new letter to the editor in Science magazine, researchers call for the global push to eliminate space junk. Their call for action is inspired by the recently signed High Seas Treaty, which sets aside a portion of the ocean for conservation and calls for environmental impact studies prior to deep ocean construction, such as mining. As signator Melissa Quinn, head of Spaceport Cornwall, says, satellites are vital to the health of our people, economy, security, and Earth itself. However, using space to benefit people and the planet is at risk. By comparing how we have treated our seas, we can be proactive before we damage the use of space for future generations. Humanity needs to take responsibility for our behaviors in space, now, not later. I encourage all leaders to take note, to recognize the significance of this next step, and to become jointly accountable. End quote. To sustainably use space, we need a multi-pronged approach that includes figuring out how to safely deorbit defunct spacecraft and debris, only launching new spacecraft with end-of-life plans in place, and working as a global community to register and organize missions to avoid collisions for as long as possible. As Imogen Napper, a research fellow at the University of Plymouth, puts it, quote, taking into consideration what we have learned from the high seas, we can avoid making the same mistakes and work collectively to prevent a tragedy of the commons in space. Without a global agreement, we could find ourselves on a similar path. End quote. The tragedy of the commons relates to how things that belong to everyone, like oceans or outer space, are cared for by no one, and are often taken advantage of by those with the most, such as large corporations, while individuals have their access or benefits reduced over time. With space, we're already seeing nations like China planning to launch swarms of satellites to reserve orbital territory for future projects as companies like OneWeb and Starlink systematically fill orbital rings. Space is a limited resource. And as this letter to the editor points out, while, quote, a number of industries and countries are starting to focus on satellite sustainability, this should be enforced to include any nation with plans to use Earth's orbit, end quote. The truth is, while humans have a long way to go before you can really call us a spacefaring species, our modern economy relies on satellites for everything from communications to commerce, and sometimes, as folks with DirecTV too often experience, the presence of clouds and atmospheric water, things like rain and snow, can mess up signals. While it can be disappointing to miss a beloved TV show, it can be devastating when an important business document or submitted class assignment is lost to the clouds. And now, a research team at Rensselaer Polytechnic Institute may have found a solution that involves blasting holes in clouds with lasers. This is not something I'd actually thought was possible. My whole career, folks have asked if we have cloud removal machines for our observatories, and I hadn't ever expected the answer to be, well, sorta. In their publication in the Journal of Applied Physics, the team writes, quote, dynamic media such as atmospheric clouds and fog form a formidable barrier to light propagation for free space optical communications. To overcome such an obstacle, we propose to make use of the acoustic properties of a laser filament coupled together with a donut-shaped signal beam. A filament generated by an ultra-fast laser is accompanied by an acoustic wave that clears a cylindrical chamber around the filament's plasma column that can mimic a transmission channel. End quote. Essentially, when the laser strikes the cloud, the light and matter interact, and this creates a shock wave, like a tiny sonic boom that clears the way for a signal to pass through the cloud. At this point, the research is still just well-worked-out theories. But as the dean of the Rensselaer School of Sciences says, quote, I expect free space optical communication technology of this type to enable hyperspeed, secure, worldwide quantum communications, end quote. The future is definitely going to involve more lasers, and I'm okay with this. After a break, we'll be back to look at the effects of zero gravity on the human body and zero sunlight on microbes. Later in the show, we'll be taking a closer look at the search for life on other worlds. Stay tuned. Okay, I have to be honest, this is a slow news week. Next week, the Lunar and Planetary Sciences Conference will be taking place, and we expect a lot of cool planetary news to be announced. This week, I'm bringing you what is starting to feel like the news of the weird, because that is the news that's happening. And if we're going to refer to the universe as weird and wonderful, sometimes we need to stare the weird right in the heart and acknowledge the weird can be just as weird as the wonderful is wonderful. Case in point, Johns Hopkins medical researchers are sending heart tissue on a chip technologies into space to, quote, monitor the tissue for changes in heart muscle cells' mitochondria, their power supply, and ability to contract in low gravity conditions, end quote. I'm an astronomer, not a biologist, and I have to admit I didn't know we had organ bits mounted on chips for research purposes. This is definitely research that is easier to do on heart muscles that aren't used by humans. This tissue launched on CRS-27, and in addition to monitoring what kinds of changes occur during zero gravity, astronauts will also be treating the heart cells with 3 FDA-approved medicines to see if they can prevent known or suspected heart cell changes that occur during long-duration spaceflight. Deeko Kim, a professor of medical engineering at Johns Hopkins University, who worked on developing this experiment, explains, quote, it's possible that what we learned from these experiments in space could also inform how we treat age-related cardiac problems, end quote. Working in space is not something our gravity-loving bodies were designed for. And we age faster and suffer vision, cognitive, skeletal, and other changes as a result of being in space. Before we can consider sending people on a multi-year trip to Mars and back again, we need to understand how to keep people healthy for long periods in space. The difficulties we see so many life forms experience in space can get frustrating when we look around our world and see life determined to exist just about everywhere. Consider the deep ocean hydrothermal vent. When I was a child, we were taught that life requires sunlight, oxygen, water, and nutrients. It turns out that wasn't at all true. As we developed better and better submersibles capable of exploring the ocean floor, we discovered a world without light, pretty much devoid of oxygen, under extreme pressure, and still capable of supporting life like nothing we'd previously imagined. The sides of hydrothermal vents are rich in sulfide-eating bacteria that live on sulfur-rich emissions of the vents. In past studies, samples of the smoke coming out of the vents had also captured some of these bacteria, called sulforamonas. It had originally been assumed that these bacteria were launched from the volcano into the surrounding water by the smoke. But researchers from a team at the Max Planck Institute for Marine Microbiology wondered if the smoke could be a rich enough environment for life to live freely circulating in the smoke. Answering this question required travel to the southwest Indian Ridge and central Arctic Ocean, and careful maneuvering of the Polar Stern remote vehicle as it traveled thousands of meters beneath the sea. These 2 hydrothermal vents are 15,000 kilometers apart and are in different deep-water current systems. Despite their separation, the smoke plume of both vents were home to genetically similar bacteria they propose naming Sulformionis pluma. These bacteria are distinct from previously studied varieties of this bacteria, and it seems to be totally fine living in the plumes. This caught my attention because we can expect moons like Europa and Enceladus at Jupiter and Saturn to have these kinds of hydrothermal vents, and this gives us one new kind of life to wonder. Is it out there too? Trying to understand what life may or may not have done on different worlds is still guesswork. There is a whimsical complexity to life that I'm very grateful to find largely absent from the physical sciences. This isn't to say things like geophysics and astrophysics aren't complicated. They are just very differently complicated. And when scientists set their minds to trying to model all the weird things going on in specific systems, it's amazing what a combination of good data, a lot of creativity, and a whole lot of careful calculations are capable of doing. In a paper that felt like an episode of some CSI Yellowstone, researchers led by Cheng-Nan Liu documented the behavior of Doublet Pool for 6 years. Doublet Pool is a hot pool near Old Faithful in Yellowstone. While less dramatic than the geysers that surround it, this pool will thump for about 10 minutes at a time every 30 minutes or so. And that or so is something worth trying to understand. Volcanically active pools and geysers are basically just really complicated steam engines. Heat from the magma beneath Yellowstone can bring water to boiling, which will cause pressure to build, which will cause geysers to go off, or pools to rumble. While this kind of a simplistic model can readily be used to explain geysers that go off like clockwork, that 30 minutes or so says something more complicated is going on. With permission from the National Park Service, researchers placed temperature and water level sensors in the pool and also recorded data on geophones that measure ground movement. They found that the pool's rumbling was affected by magma activity on longer timescales, with Doublet Pool and other features being excited by extra heat that reduced the interval to just 13 minutes in September 2018. On shorter timescales, their careful measurements allowed them to determine that wind was altering the pool's behavior. The physics behind this is really cool. And I'm just going to read you their analogy. Quote, Yellowstone's hydrothermal system is like an Instant Pot, building up heat and pressure, leading up to eruptions of geysers and other features. The researchers also noticed that silence intervals varied from day to day and even hour to hour. When they compared the weather conditions with the silence intervals, they found that wind speed over the pools was correlated with the silence interval. When wind speed was higher, the interval was longer. Nature was blowing over the top of Doublet Pool, cooling it off. End quote. In looking at geothermal systems like Yellowstone, we really have to consider all the sources of heat and also all the sources of cooling. And it turns out, when it comes to the force behind that 30-minute or so rumble at Doublet Pool, the answer is blowing in the wind. Up next, we're going to look at what it takes to look for life beyond Earth. Stay tuned. The search for life requires 3 basic things to happen. Go to another world, look someplace where the conditions don't seem too terribly terrible, and then do analysis. Remarkably, the go to another world step seems to be the easiest step. In a new study published in Nature Communications with lead author Armando Azu Bustos, researchers went to the Atacama Desert and tested their ability to find life. This extremely arid high desert has conditions vaguely similar to modern-day Mars, and like Mars' Gale Crater, where Perseverance rover explores, it appears this site, the Redstone site, is an ancient river delta. Using state-of-the-art laboratory equipment, the team were able to detect DNA from either past life or life that exists today. The DNA is unlike anything so far cataloged, which is cool. But this cool life was at the edge of what is detectable. What is detectable in a full laboratory where weight and power aren't limits to what experiments can be done. As they state in their abstract, quote, similarly low levels of organics will be hard, if not impossible, to detect in Martian rocks, depending on the instrument and technique used, end quote. Put another way, if Percy went to the Atacama Desert, he might not be able to measure life. And if life did exist on Mars, it may be beyond his ability or the ability of Mars' curiosity to detect it. And this is a fascinating result, especially within historical context. In the 1970s, NASA conducted a series of experiments with the Viking landers that were designed to look for life, and their results have led some to declare microbial life was found, some to believe it absolutely was not located, and some to think the experiments just need to be repeated. These experiments took samples of Mars soil and looked for metabolism to take place and also looked for the presence of organic materials. Oddly, while no organics were detected, there appeared to be metabolism. And for the past 47-ish years, folks have looked for chemical reactions that might mimic life, or for ways to life as we know it have existed in only one of the two experiments. In the decades since Viking, a small cadre of researchers have maintained a firm belief that Viking found life, a cadre that includes experiment designer Gilbert Levin. The majority of scientists following NASA's official release have said the experiments were inconclusive, with a strong bias of there was no life. I have to admit, this new paper makes me feel that while the results certainly seem inconclusive, it is credible to say yes, they were inconclusive, but there's no reason to lean away from the idea that life might have been inconclusively detected. As researchers, we have more reason than ever before to say, we just don't have enough evidence to confirm or deny life on Mars. The Azus Bustos paper goes on to say, quote, our results stress the importance in returning samples to Earth for conclusively addressing whether life ever existed on Mars, end quote. If we can't use Curiosity's Mars Science Laboratory skills to test for life, at least we know Percy is out there collecting samples that will hopefully make it back to Earth for analysis. We just need to get a mission built, launched, and collect the samples, and successfully launch the samples back off of Mars. It's going to be a while, folks, but the missions are being planned at least. And the time that it takes us to plan those missions is also time that we can use to improve our search for life. And here is where I like to say the Atacama Desert seems to be teeming with folks trying to find life on Mars. In a completely different study, researchers led by Kimberly Warren Rhodes went to a different part of Atacama and mapped out the distribution of life on salt domes, rocks, and crystals at Salar del Pajonas. They then trained machine learning models to recognize the patterns and rules behind these distributions so they could make probability maps of where life should exist. Researchers found biosignatures of life 87.5% of the time they looked where the software recommended. This is compared to finding life just 10% of the time when they randomly looked somewhere. Put another way, by focusing on the places the machine learning software recommended, they could reduce the area that needed to be searched by 97%. While this research seems like a promising way to accelerate the search for life on Mars, there are some important questions that still need to be explored. On one hand, will the rules they found for life in one desert on Earth also be relevant for other ecosystems? In future tests, this team will be looking to see if their software can aid them in the search for ancient stromatolite fossils and halite microbiomes. If the current successes can be replicated in other Earth climates, we still can't know if Mars life, if it has or does exist, follows the same rules, but it at least gives us a starting point on where to look for life. The reality is, life on Earth is hugely varied. The only real rules are life requires nutrients to metabolize, a source of heat to enable chemical reactions, and a solvent like water to provide a place for those chemical reactions to take place. Here on Earth, we've found life living on deep sea hydrothermal vents, in the soils of extremely deep mines, in hot springs, and even in radioactive spill sites. It seems that if chemical reactions can find a way, life can find a way, at least on our planet. We have a sample of one. If we are unable to find life in any of the other potentially habitable places in our solar system, it just might be that life is extremely rare. But if we do find it in fossils or happily metabolizing on Mars or living in the subsurface seas and any of the solar system's icy moons, if someone makes what would be the most amazing discovery of astronomy to date, then we may just be able to say that it's easy to imagine life out there waiting to be discovered among the stars. While the conditions for life, nutrients, a solvent, and heat, aren't all that complex, intelligence seems to require one additional factor: stability. It is hard to imagine life having the ability to evolve from microbes to complex multicellular life without the kind of long-term stability that provides time for life forms to experiment with form, to find those mutations that increase the chances of success. Here on Earth, we have a many billions year history of episodic evolution and mass extinctions. All in all, however, our planet has mostly stayed about the same distance from the sun and has maintained temperatures that allow liquid seas and forests, at least in equatorial regions. This stability is due in part to our world's relatively stable orbit. But there was nothing dictating it had to be that way. Looking out across the solar system, it was recognized early on that the spacing between planets fits a nice trend, with each new world falling roughly twice as far from the sun as the world before it. Known as Bode's Law or the Titus Bode Law, this relationship predicted the location of the asteroid belt, and may be part of what led so many early astronomers to suggest the asteroids are a destroyed planet or a planet that wasn't able to finish forming. We use the Earth's distance from the sun as a unit of measure called the astronomical unit. And according to Bode's law, the next planet should be at 2 AU. Now, I have to interject, there's no physical reason for Bode's law to be a law, and we're not seeing this applying to other solar systems. It's just a trend. Anyways, the asteroid belt actually spans from about 2 to 3.5 astronomical units from the sun. And the reality is, the mass of the asteroid belt is just 3% of the mass of Earth's moon. And while it is safe to say these space rocks are objects that failed to become planets, it wasn't as much a group effort as each rock failing individually to gather up enough mass to become a world. What if the solar system did have a planet located where we see the asteroid belt? What would have been different if Bode's law did work out? It turns out putting a world in that region of the solar system could be catastrophic, not just to life, but to our planet as a whole. Looking around our galaxy, we find that worlds larger than Earth but smaller than Neptune are actually quite common. If one of these super Earths were to go into this gap, it could, it turns out, destabilize the entire solar system. A new paper by Stephen Kane in the Planetary Science Journal shows that this kind of an extra mass would alter Jupiter's orbit just enough to, quote, ultimately eject Mercury and Venus, as well as Earth, from the solar system. It could destabilize the orbits of Uranus and Neptune, tossing them into outer space as well, end quote. Lower mass planets would be less toxic, but the smallest deviations could still create chaos. And it turns out it really is all about location, location, location. Per the paper, quote, system dynamics remain largely unaffected when the additional planet is placed near 3AU. Mercury experiences substantial instability when the additional planet lies in the range 3.1 to 4AU. And perturbations to the Martian orbit primarily result when the additional planet lies in the range 2 to 2.7 AU. Put another way, if you put a spare planet precisely between 2.7 and 3 astronomical units from the Sun, things might be okay. But anywhere else, chaos. And if our world were flung out of our solar system, I feel safe saying life as we know it wouldn't be here. So next time someone says the asteroid belt is a failed planet, let them know, first of all, it's not enough mass to be a failed planet. And if there had been a planet there probably wouldn't be an us here. After a break, we'll be back to look at this week's aerospace news. Stay tuned. While reading a news release, I came across one of those straightforward sentences that really makes it clear there is a problem that needs to be solved. That sentence read, quote, "While people have managed to put men on the moon, they haven't figured out how to keep them clean there." End quote. Moon dust is one of the nastiest naturally occurring substances. Like pet hair, it electrostatically sticks to everything. Like dust on Earth, it is super fine and gets into everything. And unlike anything you've hopefully encountered, moon dust is as sharp as glass. Moon dust is the sharp bits of rock that are knocked free when micrometeorites or large impactors hit the moon. Without wind, rain, and flowing water to tumble and smooth the dust, it just sits on the moon, sharply waiting for the soft-skinned astronaut to give it a ride into a capsule where it can make everyone miserable. The Apollo astronauts didn't have a good time dealing with this stowaway grit. And as NASA looks to return astronauts to the moon, effort and funding are going into testing new ways to keep the lunar dust away from humans. One method is to have spacesuits mounted outside and astronauts treat the spacesuits like an airlock. That method, however, can't always be used. And this is where folks are getting fancy with a space-age power washing kind of idea. Washington State University researchers report in the journal Asta Astronomica that they have been using a sprayer with liquid nitrogen to clean spacesuits that are covered in simulated moon dust. The sprayer removed 98% of the dust, and the spacesuits could be sprayed down 75 times before damaging wear and tear was observed. The prior method, trying to brush the dust off, led to damage after a single brushing. This research was performed in a vacuum chamber at Earth gravity as part of NASA's Breakthrough Innovative and Game-Changing Idea Challenge. The team is now looking for further funding to test things in even more moon-like settings. Hopefully, in the not-too-distant future, Eric will be here telling us about tests done in space. For now, let's hear about the latest packs of satellites carried into orbit. I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. On March 16th, Rocket Lab conducted its second Electron flight from U.S. soil, carrying two more Raider satellites for Capella Space from LC-2 at the Mid-Atlantic Regional Spaceport in Wallops Island, Virginia. The launch was successful and no recovery attempt was made. It was delayed several days by high upper-level wind shear reading on March 11th. In one of the recent episodes, we talked about Relativity Space and the first launch of their new rocket, Terran 1, on a mission named Good Luck, Have Fun. Terran 1 is the first orbital rocket that is largely 3D printed metal. Metal 3D printing is a relatively new technology, and Relativity Space's printer is basically a huge welder that fuses metal wire together in layers. It's the largest of its kind. Relativity Space says that this approach reduces costs by simplifying the supply chain and decreasing the number of parts in its rocket by 100 times. The first launch attempt came very close, aborting at just T-minus 0.5 seconds because the flight computer detected something out of specs. The second launch attempt was scrubbed at about T-minus 70 seconds due to a slight underpressure of the liquid oxygen tank in the second stage. Even though it was just 1 psi below the spec, Relativity made the decision to scrub the launch attempt because even 1 psi can make the difference between success and failure. On March 22nd, they were ready to try again. After stopping the countdown clock a couple of times for things like a rogue boat in the exclusion zone and upper-level winds being too high, the countdown clock finally reached zero and Terran 1 started up its 9 methane-powered engines and headed toward space. Because this was the development mission, Relativity Space heavily managed expectations, saying that it would be good if the rocket made it through max Q, the point at which the rocket experiences the maximum dynamic pressure due to air resistance and its velocity, and is considered one of the riskiest points in the flight shortly after launch. Completing the first phase of flight and the starting of the second stage was considered a bonus. The rocket itself had no payload fairing, as it didn't have a payload on the flight, common on most first flights of a new rocket. Instead, it carried the first ever metal printed by Relativity Space as a test mass. Unfortunately, it did not make it into orbit. The first stage of flight was successful, up to separation, but the second stage engine did not start up correctly, and the mission was lost. The coverage concluded with the hosts remarking on just how much they had succeeded with this first flight. Despite not making it into orbit, Relativity Space considers this first flight a success. We're looking forward to their next flight once they've had a chance to analyze the data and figure out why the second stage engine did not start. And, when it happens, we'll tell you all about it here on Escape Velocity Space News. The race to be the first rocket powered by liquid methane to reach orbit is still anyone's game, with an attempt by Chinese company Landspace back in December failing to reach orbit, Hyundai's Vulcan deep in integrated testing at the launch pad but not ready yet, and SpaceX Starship being Starship. As of when we're recording this episode, Vulcan has a pretty firm launch date, but we're not going to jinx it by mentioning it on air. You'll just have to watch our coverage after it happens. In even more good news for Rocket Lab, their second launch in as many weeks was successful. Rocket Lab sent up another Electron, this time from their usual home base in New Zealand. On board was another pair of satellites, this time for Black Sky Global, a company that operates a constellation of optical imaging satellites. These will be the 8th and 9th satellites the company has successfully launched for Black Sky. A further 2 failed to reach orbit in 2021 after the second stage engine thrust vector control failed. Unlike the mission we started this segment with, Rocket Lab did another recovery experiment, fishing the first stage out of the ocean after launch when it splashed down under a parachute. To wrap up the launches this week, SpaceX launched 2 more batches of Starlinks, totaling around 100 satellites on March 17th and 24th, and SES-18 and 19 on March 17th. The latter 2 satellites were launched together, and complete SES's move out of the lower part of the Ka band to make room for terrestrial 5G cell phone networks. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 24 launches, China 11, Kazakhstan 4, Japan 2, and India, New Zealand, and the United Kingdom each have had 1. Of those 44 launches, there have been 4 failures, reminding us that space is hard.
Thanks, Eric. The life of an astronaut isn't an easy one, and a lot of the basic kindnesses we get to have on Earth just aren't available to astronauts. There is no going to the bathroom in complete privacy. There is no getting to just take a hot shower at the end of the day. And there hasn't been a nice hot cup of coffee to start the day, at least until now. In a tweet from the ISS research account on March 2nd, NASA showed off its newly developed space cups, which use capillary action to keep beverages at the bottom of the cup and allow liquid to flow along a channel to the astronaut's mouth. These cups aren't something you're going to see on sale at your local box store anytime soon. They are best described as utilitarian and ugly in a non-endearing sort of way. Nevertheless, as someone who lives by the power of caffeine, if the choice was no coffee, or a weird Capri Sun-like bulb of coffee, or a really ugly plastic cup, I'm going for the really weird plastic cup. Here is to the little things in life, like coffee. And that is it for now. Good night, everyone, and remember to go out and look up.